Alright, welcome. So in this video we are going to talk about power series and when they converge. So in the last video we talked about power series more generally as a sum from n equals 0 to infinity of c sub n times x to the n. This time I'm going to extend it a little further and talk about a power series centered at a specific point. So we're going to talk about it being centered at x equals a, and this time instead of x to the n, we have x minus a to the n. So this is just to say that a is sort of the point we are starting at. So if you plug in a for x, we're getting 0. So that's our sort of center point. So it's called the power series centered at x equals a because the radius of convergence is centered at x equals a. And really, you could think of this as the interval of convergence being centered at x equals a. Basically, if we have that value a, there's going to be some area around it where x is convergent in the interval. So if we look at x values in that interval, the power series converges. So that might be like a plus something and a minus something. From those two values, that's where the power series is convergent. Then outside of that area is where it's divergent. Okay, so for solving problems, knowing why it's called centered at x equals a isn't too important. I just like to think of that x equals a value as the starting point. So when we plug in a, we get 0. That's sort of our beginning location that we're working from. Okay, so when we have power series in this new form where it's centered at x equals a, we can use the ratio test to determine for which x values it's going to converge. So in general, for the ratio test, we look at the limit of subsequent terms as we go further and further into the series. So the limit as k approaches infinity of the absolute value of a sub k plus 1 over a sub k. And so here we're going to be looking at subsequent terms in the power series. So a sub k is c sub k times k minus a to the k power, and a sub k plus 1 is the next term, so c sub k plus 1 times x minus a to the k plus 1. And so depending on the problem, we're going to have different coefficients c sub k and c sub k plus 1, but the idea is that we're looking still at subsequent terms and they're going to be of this form. So once we have taken that limit and we've determined which values of x make it work, make it less than 1 for convergence, this is called the interval of convergence. So really here, there's a lot of words, I've said a lot of things, but we're really just taking power series and applying the ratio test to them. So rather than just looking at other series with real numbers in them, now we're looking at power series with variables and applying the same ratio test to determine for which x values it converges. So on which x values is the power series going to converge to a specific thing. Okay, so rather than doing too many examples with you, I'm just going to do one example and I'm going to show you how it really is very similar to just computing the ratio test for a series that isn't a power series. There's a little bit to be careful about with the absolute values, and there are some more details here that I'm actually leaving out just to make this a little easier. I really just want you to get the idea that we can apply the ratio test to power series as well. That's the main point I'm trying to get across. So let's look at this series from n equals 0 to infinity of x minus 2 to the n power over 5 to the n minus 1. Now if it helps, you could factor out that 1 over 5 to the n minus 1, so you really see that this is a power series. That 1 over 5 to the n minus 1 is the coefficient, and then the x minus 2 to the n is the x to the n portion. So it's x minus a is 2, to the n. Now to determine where this power series converges, we're going to use the ratio test. So first we substitute in k plus 1, and we divide it by what happens when we substitute in k. We're looking at subsequent terms here. And to simplify, I do the same thing I do with the ratio test. I multiply by the reciprocal. So I'm going to rewrite x minus 2 to the k plus 1 as x minus 2 to the k times x minus 2. Similarly, for 5 to the k minus 1, I'm writing it as 5 to the k times 5 to the negative 1. And I'll leave the denominators the same. So I'm seeing that the x minus 2 to the k's cancel and the 5 to the k's cancel. So I'm just left with x minus 2 times 5 to the negative 1. That 5 to the negative 1 is 1/5. And so I'm getting x minus 2 over 5. Now, this is my R value, my ratio of subsequent terms, and I want to know what happens to this ratio as k approaches infinity. So here we actually got rid of all of the k values, so we don't have a limit anymore. We're just looking at the absolute value of x minus 2 over 5, and we want to know where that's less than 1. I'm going to take off the absolute value on the 5 since 5 is already positive. And so we can conclude that this power series converges when the absolute value of x minus 2 over 5 is less than 1. Now all we need to do is just solve this inequality to determine for which values of x this is true. Okay, so to do this, I'm going to multiply the 5 over, and so I need to solve the inequality absolute value of x minus 2 is less than 5. So doing this involves solving two separate inequalities. So I'm looking at the negative and the positive version of 5. I'm looking at where x minus 2 is greater than negative 5, and where x minus 2 is less than 5. So I'm getting that x is greater than negative 3, or x is less than 7. And so I'm determining that this series converges between negative 3 and 7, which is the interval from negative 3 to 7. Okay, so I know I didn't go too into depth here. I really just want you to know that we can talk about power series convergence. We could go way into depth about it, and we could do lots of examples, but I really just think it's important to know that we can look at where it converges, and that is going on behind the scenes a lot of the times when we're dealing with power series, and in turn when we start dealing with Taylor series. That's it for this video. Thanks so much for watching, and I will talk to you in the next one.